This is joint work with Ronen Eldan and with my PhD advisor, Ohad Shamer. So on a higher level, this talk will discuss the approximation capabilities of neural networks. More specifically, what can we approximate efficiently using various architectures? We consider fully connected feed-forward neural networks. Here we see a more concrete example of a one hidden layer neural network. We have the weights of the output neuron, the VIs, and the weights of the hidden layer, the WIs, and the bias terms. And recently, several papers showed a result that is now called depth 2 versus depth 3 separations that basically says that there are functions that can be approximated efficiently using a network of width polynomial in both the input dimension D and the accuracy parameter epsilon to accuracy epsilon. However, if we want to approximate those functions using only a depth 2 network, then we will need width that is at least exponential in the input dimension D. So the interesting thing about these results is that all these results use or can be reduced to radial functions. That is, functions that depend on their input solely via its norm. So here we see the underlying intuition for considering radial functions for such results. On the left, we see a single Rayleigh neuron. This is, in fact, a function that differs only in a single direction. On the right, we see a radial function. This is quite the opposite. This is a function that differs in all directions. So the underlying intuition, if we want to approximate a function that differs in all directions using linear combinations of functions that differ only in a single direction, then we will need to use many such functions. So another interesting property we have regarding the functions that were used to show these kinds of results is that they have a Lifshitz constant that scales polynomially with the input dimension D. In general, this is an undesired property because it can be shown that gradient-based methods have a hard time learning functions with large Lifshitz constants. And many learning problems have dependencies on the Lifshitz constants, so we want it as small as possible. So the question that we wanted to ask is, can we show such separation results, but for functions that have a constant Lifshitz parameter that does not scale with the input dimension D? But after asking this question, realized that things are more complicated than that. And the reason that things are more complicated than that is because we can always take a function with some Lifshitz parameter, and we can rescale it linearly in a way that will make the function have a constant Lifshitz parameter. And at the same time, we'll need to, and this will come at the cost of having lower accuracy. So any approximability result can be translated for a Lifshitz, for a function with a large Lifshitz constant, can be translated to an approximability result with a constant Lifshitz parameter, as we can see here in the displayed equation. So similarly, we can also show that you can trade off the radius of the domain of approximation with the Lifshitz parameter. So we need to refine our question. Suppose we have that the accuracy parameter epsilon represents also the Lifshitz constant and the radius of domain of approximation. Then we are asking the following question: can we show such separation results for approximating functions which have a constant Lifshitz parameter on a constant constantly bounded domain? And we want all these quantities to be independent of the input dimension D. So the result we have shown is that the answer is no. We cannot obtain such separation results, at least not for radial functions. And the reason we can't is because if we do fix these quantities, then we can approximate any continuous radial function to accuracy epsilon using a network that scales, that its width scales only polynomially in D. So later we considered the complementary setting where we fix the input dimension D. And building on a result by Klusovsky and Baran, we showed that we can do this, we can approximate this efficiently using width which scales only polynomially in 1 over epsilon. So what is the conclusion here? The paper asks what is being separated, and the answer is that both parameters are being separated. If we fix either quantity, either d or epsilon, then we are able to get an efficient polynomial dependence on the other. So if we want to show such separation results having exponential dependence on the input dimensions when epsilon is fixed, then we would need to use fundamentally different techniques than the ones we know so far, if at all possible. Additionally, we also show, considering known separation results and reducing to these results, we show that we cannot have dependence polynomial in both the input dimension d and 1 over epsilon. Here to the left, we see reduction to a result by Danieli. This function is a function that cannot be approximated efficiently with polynomial dependence on both parameters. And this approximation is done on a compact domain and using exponentially bounded weights. And to the right, we see the function that cannot be approximated using a reduction to the result of Eldon and Shamir that cannot be approximated with respect to a distribution that has unbounded support, but with no bound on the weights. As an additional artifact for our main proof technique, we can also show that there are cases where we can approximate efficiently in both parameters. More specifically, we show this for functions that are even powers of the norm of the input. Okay, so now I want to go over the high-level proof idea for the main contribution for having constant accuracy parameter epsilon and showing that we can build a network of width polynomial in the input dimension d. So first we take one hidden layer network. We fix the weights of the output neuron to be 1 over n, and we set all bias terms to 0, and we draw all the neurons of the first hidden layer, of the hidden layer, to be uniformly at random from the unit sphere. So since we have this symmetric distribution over all the neurons, we would expect with a very wide network that this will gradually converge to a radial function. And this is indeed what happens, and we can compute the expected function we get over the randomness of the weights and show that this is indeed a radial function. And what we do next is we use a concentration of measure argument to show that with high probability we will get a good approximation, which means that there must exist a set of weights which provides this good approximation. And the last step is to show that linear combinations of this function that we approximate, this radial function, can approximate any continuous radial function. Where the main challenge in this proof is to basically keep track of the dependence of the width on the input dimension and show that it always remains polynomial. So to summarize this talk, the take-home message here is that if we want to show separation results between depth 2 and depth 3, and we want the dependence on the input dimension to become exponential, all other quantities are fixed, then we will need to consider fundamentally different techniques than the ones that are currently known, if such a result is at all possible. So thank you, and I would gladly take any questions.
I think so. Let's see.